A warm welcome to the respected dignitaries and faculty members. Myself, Sridipti, pursuing third year from the Department of Triply from SP Colleges. Welcome to the short-term training program on research trends in renewable photovoltaic system and its research challenges. A warm welcome to the respected dignitaries and faculty members. Myself, Sridipti, pursuing third year from the Department of Triply from SV Colleges. Short-term training program on research trends in renewable photovoltaic system and its research challenges. I would like to invite a man of distinct vision and a fountainhead of illuminating ideas to Triply Department. Welcome. Now, I consider it a great honor to speak about our chief guest, Dr. C. Dhananjaylu Garu. He is presently working as a senior assistant professor in Vellore Institute of Technology. He is BTech in Electronics and Communication Engineering at Madanapalli Institute of Technology and Science, Indian Institute of Technology, Chennai, and his PhD in Power Electronics, Vellore Institute of Technology. He has served various administrative positions like SET Conference Coordinator, Timetable Coordinator, Academic Coordinator. Sir has published 18 national and international journals and attended 2 national and international conferences. His areas of interest are multi-level inverters, optimal control of electric soft switching techniques,
Hello. Hello. Hello, you are able to hear my voice? Hello.
Yes, sir.
Your voice is audible.
Yes, sir. Yes.
Yes, sir.
Yes. Please try it. Hold it. Hold on. Yes, you are able to hear my voice? Hello.
Yes, sir.
Yeah, thank you. Yeah, now it is okay, I think so, right?
Yes, sir.
Yes, fine.
Yes, sir. Yes.
Yeah. Good afternoon, everyone. Myself, Dr. Dhananjay Lucy. Now I'll present a brief overview of a multi-level inverter with reduced circuit components for solar PV applications. Today's the technological world is completely associated with electricity, but availability of electric source is very low. Due to this, the demand for renewable energy system is rising rapidly with the depletion of fossil fuels. But issue with renewable energy system is not reliable, high harmonic, with unstable. But 90% of industrial and domestic loads all are in AC in nature. To interface these power sources with to interface these power sources, inverter is mandatory. But the power obtaining from the solar fuel cell is DC source, whereas wind is AC source. The power obtaining from the solar PV is not constant and it will produce as the low voltage. In order to enhance the DC linking lower voltage to the higher DC linking voltage, converter is mandatory. So here the maximum sizing and quality of the converter, inverter topologies has enough scope for research. When it comes to inverter, circuit components and THD is the major issue. High harmonics in the output, it will damages the load. Additional filter is required for elimination of ripples. If more circuit components are involved, it will causes the switching losses and conduction losses, and also it will increase the power losses. Therefore, it will decreases the efficiency. So when it comes to boost converter, the boost converter is integrated with the inverter for generation of quality AC output waveform. Issues with converter is we need to enhance the DC linking voltage to the maximum from the solar PV models. And we need to design of MPPT is one of the major issue. And the converter output on converter efficiency is also very poor. So these are the major issue when it comes to boost converter. So perfect solution for this. So multi-level inverter topologies via minimal number of components and to reduce the complexity with PWM technique. If more circuit components are involved, less computational burden, that is nothing but easy digital control to interface MATLAB. That means you can use FPGA controller and D-space controller as well as DSM wave, high quality sine wave with reduced THD contents as IEEE standard. This is the one of the objective. And the stable operation under dynamic load conditions. This is a key factor in inverters. You need to test your inverter with the linear and non-linear loads. So these are the major issues. So that is objectives. When it comes to boost converter, as I said, we need to enhance DC linking voltage to the maximum from the solar PV. So effective MPPT technique extract energy from the solar PV models, and converter output should be improved. And this is the overall structure of PV models. It is integrated with boost converter, and MLA topologies. And if you see here, and here the PV panel, we are extracting maximum energy from the solar panel, and it is fed to the boost converter. The boost converter will boost the output voltage, and it should be fed to the inverter. Inverter will convert DC to AC. So here you can develop new MLAs, that is multi-level inverters with reduced number of components, and it should be connected to the grid. This is one of the major, yes?
Sir, PPT is not visible, sir.
PPT, what happened?
It is not visible, sir.
I am sharing. Hello? You are not?
No, sir. PPT is not visible.
Oh God. I think for me it is.
It is not open, sir, actually.
It's not open?
Okay, yes, sir.
Okay. 1 minute. Right now, fuzzy fuels. Issues with renewable energy system is not a system. But 90% of industrial and domestic loads all are in AC in nature. To interface these power sources, inverter is mandatory. But the power obtained from the solar and fuel cell is DC source, whereas wind is AC source. The power obtaining from the solar PV is not constant, and it will produce as the low voltage. In order to enhance the power to the higher DC linking voltage, convert is mandatory. The maximum sizing and quality of the inverter topology has enough scope for research. When it comes to inverter, the circuit components THD is the major issue. It will damage the load. Additional filter component is required to eliminate the harmonics, and more circuit components are involved, so it will increase the conduction losses and switching losses, and also it will increase the power losses, therefore it will decrease the efficiency. So when it comes to boost converter is integrated with the inverter for generation of quality AC output waveform. Issues with converter, you need to enhance the DC linking voltage to the maximum from the solar PV. And design of MPPT is one of the key factor, and we need to converter with higher efficiency. So these are the major issues when it comes to boost converter. So perfect solution for this is we need to implement multi-level inverter topologies by a minimal number of components to reduce the complexity with the PWM technique. The more circuit components are involved, it will generation of PWM technique is quite difficult. Less computational burden and easy digital control with MATLAB interface. That means you can propose with a D-space controller or PGA control to interface MATLAB. High quality sine wave must be obtained with reduced number of reduced PhD content as per the IEEE standard. Stable operation under dynamic load conditions. This is the key factor with respect to inverter. We need to test your inverter with non-linear loads as well as linear loads with dynamic load conditions. And to provide a perfect solution for the boost converter topology, as I said here, we need to enhance the DC linking voltage to the maximum from the solar PV. And effective MPPT technique to extract energy from the PV panel. And the MPPT technique, by using that, we need to get high efficiency. These are the objectives. Still, you can concentrate. So this is the overall structure of MLI is integrated with boost converter for solar PV applications. When it comes to solar PV, solar power is generation. It consists of solar PV panels, whereas the output voltage of the solar panel is fed to the DC link through the DC converter. The voltage from the DC link is fed to the DC to AC inverter to the load. The output of the solar panel is not constant, and it changes according to the solar radiations and temperature. Therefore, the more for the efficient operation of PV panel, even under various climate changes, it is essential to extract the maximum power from these PV models. So we need to use effective MPPT technique extract the energy from the solar panel. So, and when it comes to converter, as I said, we need to enhance the DC linking voltage to the maximum by employing with DC converter with high gain. So these are the major issue. When it comes to MLIs, as I said, we need to convert DC to AC. So to get the quality output sine wave. So now I'm going to concentrate. I'm going to give brief overview of solar PV MPPT design as well as with 4 types of converters, and I'll show you different type of multi-level inverters with the reduced number of components. So when it comes to solar PV, as I said here, so this is the equivalent circuit of solar PV. It consists of internal resistance, and it is connected to diodes in series parallel combination is known as equivalent circuit. Whereas IPV, VPE is a solar voltage and solar current from the solar PV. So here the number of components are see the graph here, VI characteristic graph. So the PV is fed to the inverter. So you need to get maximum power point, that is maximum power MPPT technique. You need to extract the maximum power at IMP and VMP. And when it comes to MPPT technique, now I am going to propose with simple PNO technique to extract the maximum power. You can start. This is a flow chart for MPPT technique to PNO algorithm, and you can initialize the data, and you can that is VPV, IPV, and you can calculate delta V and delta P, and delta P is equal to 0. So yes, it goes to starting point. If no, if delta P is greater than 0, yes, and it will goes to delta V is, it will check delta V is less than 0, and it will increase the duty cycle. If not, it will increase the duty cycle. This it will repeats. If delta V is equal to 0, no, and it goes to delta V is greater than 0, and it goes to delta V is greater than 0, and it will decrease the duty cycle. If not, it will increase the duty cycle. So this will repeat until we'll get maximum power. That means you have to follow A to G steps for extract the maximum power. So IPV, VPV model values are gathered from the PV models, and the power is calculated from the values are stored. The values are recorded from the next consecutive K plus 1 instant repeat step A. That means the values got from K plus 1 instant are subtracted from the values got Kth instant. Right side, the slope is negative. Positive, that is dP by dV is greater than 0. Therefore, the lesser duty cycle will occur at the right side of the curve, and high duty cycle will occur at the right hand side of the curve. Based on the polarity of the slope, after subtraction, the algorithm will dissect the changes in the duty cycle. So it is a continuous process to extract the maximum power. So when it comes to conventional boost converter, so this is a simple boost converter. So by using it is having consists of one inductor value and one switch, one diode. I think you can have one design equations. So I am going to show the design equations for you. You are able to see one more slide. Yes. So this is a boost converter design. So let us take here. It is consists of inductor and diode and capacitor and resistor. When switch is on, so that means inductor will charge, and this is when switch is closed. That means here characteristic is open or closed. So here it will act as a short circuit. Whatever energy we have here, it will transpose to the load side. So by applying KVL, we will get Vg equal to VL and IC equal to minus V0 by VR. So there is in switch is closed. When switch is open, so obviously this is flat as open circuit here, and whatever energy it will transfer to the output voltage. Again, you can apply Kirchhoff voltage law to get the ripple currents and ripple voltage. So here minus Vg plus VL plus O, whereas VL is the Vg minus V0. By applying KCL, that is Kirchhoff's current law, we will get the current. So IL equal to IC plus I0. IL is IC plus V0 by VR, and IC is IL minus V0 by R. Yes.
Sir, slide is not visible. This is a slide conventional boost converter. There is no design.
Okay, 1 minute, please. Now you are able to see, please.
Yes, sir.
Yeah. I think this is the design of boost converter. That means switch is on. Let us take here example here. When switch is closed, diode is open circuit, and this the voltage of to the inductor will charge, and inductor current link is the during the state. So that is Vg equal to VL. That means inductor will charge through when switch will close, and then you can apply switch off voltage law, and we will get Vg equal to VL and IC equal to minus V0 by VR. And this is for mode 1. And switch is open, and so again it will whatever energy is there across the inductor, it will transfer to the load. It means apply switch off voltage law, that is minus Vg plus VL plus V0. So you get equal to 0. And inductor current is voltage is Vg minus V0. And we will apply switch off current law, IL equal to IC plus I0. IL is IC plus V0 by R. And we'll get IC is IL minus V0 by R. And V0 equal to F into Vin plus duty ratio. And you can calculate the delta IL and delta VC for greater than 0, that is for conduction mode and ripple mode. So for IC of T is average is equal to 0, then you can calculate the average ripple current, that is minus V0 by R into delta, that is D into TS plus IL minus V0 by R, that is 1 minus D into TS is equal to 0. Then you can calculate the IL value, inductor current, that is V0 by R, that is 1 minus, that is 1 by 1 minus D. So whereas IL equal to I0 by 1 minus D. So whereas I0 equal to V0 by R. So you can calculate I0 based on the I0, V0, you can decide values of L value and capacitor values. So similarly, you can calculate inductor values. So when VL equal to average and T, you can find V0 by Vg. So obviously you'll get gain here, that is 1 by 1 minus D. So that is the duty ratio for V0 equal to that is the voltage is equal to Vg. Vg is nothing but here input voltage, or you can call it as VPV. VP is nothing but 1 by 1 minus D. So based on these values, you can you can calculate the values. Here gain versus duty ratio, this is the duty ratio formula. So you can calculate the maximum steady state, you can calculate IL and you can calculate the ripples by using slope. This is the IL max and IL minimum. From there you can calculate the steady state mode, you can calculate the values of delta V and delta L. Based on the ripple current and the ripple voltage, you can calculate the, directly I'll give you values, you can directly fix the ripple current and ripple voltage. Based on that ripple current and ripple voltage, you can calculate, and based on that you can fix your output voltage. The output voltage is related with the duty cycle. So fix the duty cycle. According to duty cycle, you can calculate the output voltage. So when it comes to boost converter, I'll give you directly values. You can need to derive the derivation part. So we'll repeat first, calculate the ripple current and ripple voltage. Then followed by you can fix your output voltage and fix the input voltage. Based on that, you can fix the duty cycle and you can calculate inductor value and capacitor values. So a SEPI converter. So this is single end primary inductor converter. So ripple current and ripple voltage. Based on the ripple voltage and ripple current, you can calculate inductor value and capacitor values. Here it consists of 2 inductors and 2 capacitors, 1 diode, 1 switch. And based on the duty cycle, you can fix here. Duty cycle is different from conventional cycle is D equal to V0 by V0 plus Vn. So based on that ripple current, you can calculate inductor value. So L1 equal to Vn into D upon the fundamental switching frequency, that is Fs into delta. Delta I is nothing but ripple current. You can calculate, as I said, there is a derivation is there. From the derivation, you can calculate the ripple current. Based on the ripple current, you can calculate the inductor values. Similarly, L2 is Vn into 1 minus D, almost all similar, divided by a fundamental frequency with the ripple current. So we'll get the inductor values. Based on the capacitor, also same. The C1 you can calculate I0 into D upon Fs into delta V. This is the ripple voltage. Based on the ripple voltage, you can calculate the capacitor values. So this is a simple I have designed with the safety converter with the input voltage is for 50 volts, and I need to enhance this output voltage into 400 volts, and I have considered duty cycle into 90%. Remaining is switching frequency is 50 kilohertz. So you can fix your similarly Leo converter. This is a simple structure. You can get ripple current and ripple voltage are zero in here. This is a simple structure, and you can calculate duty ratio. Again here, based on the duty ratio, you can calculate the values of V naught, and the duty cycle is here V naught equal to V naught minus 2 into Vn by V naught minus Vn. Based on the ripple current, again you need to calculate again here inductor and capacitor values. So here inductor value is Vn into D upon the switching frequency into ripple current. Then you will get the inductor value. So similarly capacitor, you can calculate C1, C2 and V0 by D and divided by Fs into D into V, that is ripple voltage into resistor value. You can calculate the capacitors. So again here I have considered the input voltage 52 volts, and I have fixed the duty ratio with 87%. One diode and capacitors. So what is the advantages using switched capacitor unit? Here why that means here when capacitor, that is when switch S1 will turn on, the capacitor will charge. When that is switch 2 will turn on, capacitor will discharge. That means during discharge time it will boost the output voltage. So that is having switched capacitor unit with one DC source. That means if you see that capacitor charging, the capacitor is charging through diode. That means here the output voltage will be V. That means if you see that S1 input voltage is, let us take fix 1 volt. Whenever V1 equal to 1 volt, the capacitor will charge, then output voltage will be Vc. So that means you see that the capacitor is charging, that that is during charging time we are getting Vc. For discharging time, if you see that through S1 the capacitor will discharge, that time it will double the output voltage. That means it will have output voltage V1 plus Vc1. So during discharge time we are able to get 2V. That means during the switched capacitor's advantage here, during it will boost the output voltage according to design. So this is one advantage having a switched capacitor unit. So this here was by using one simple switched capacitor. You see that here S1 will charge and we are getting output voltage Vc, and when discharging time we are getting a 2V. That means output voltage is doubles. By having a 2 switched capacitor unit, by employing 6 switches, we are able 10 switches. That means total switches. We are able to generate 70 levels. So compared to a hybrid cascaded multi-level uniter, there we have 24 switches, and we are generating 70 levels in symmetric mode. Here, by employing only 10 switches, we are able to generate 70 levels. So this is an arrangement we have by using this switched capacitor unit. We are able to generate 70 levels. So see that this is a unit 1 and unit 2. Unit 1, let us take, I have fixed Vc1 is 12 volts, 12.5 volts. And during discharge time, see that V0 is the output voltage doubles. That means 12.5 we are achieving 20 waveform. We have tested with mode, we are able to generate 25 levels. So this is another one. This is has been published in Wiley Journal recently. This is, as I said here, see that this is the proposed developed MLI. Here, this is the HBridge inverter. This is the basic 16 level asymmetrical multi-level inverter. Here I have considered 3 DC sources by employing 5 unidirectional switches. We are able to generate 16 positive levels. So this circuit will give only 16 positive levels. But by employing the HBridge inverter, as I said, the HBridge inverter will give the polarity changes, polarity generation. So by employing HBridge inverter, we are able to generate total number of levels, 31 levels. So here we have only 3 DC sources. By employing HBridge inverter as well as this proposed inverter, we are able to generate 31 levels. So again here, if you are having expected waveform, always we need to generate gate pulses while having more circuit components are involved. It is quite difficult to generate PWM technique. So we need to have expected output waveform. By expected waveform, you can generate a PWM technique. So based on I think there are so many PWM techniques. The best one is here by using a staircase PWM technique. You can cascade with step by step. You can able to generate more number of levels. This is a computational burden also is very less. You can easily generate the gate pulses. And if number of levels are increasing and you have more number of circuit components are involved, it is very difficult to generate PWM technique. So based on the firing angles, by using round robin condition, we are able to generate switching that is gate pulses to the switches. So this is the expected waveform. As I said here, first I have simulated with 16 positive output voltage levels. So see that expected output wave, that is simulated output waveform. This is the experimental output waveform. So this is, we have tested with, again here, we have extracted a simulation output waveform. It shows that 31 output voltage levels and TH is drastically reduced. And see that we have tested with modulation index. We have varied modulation index. Based on the modulation index also, you will get a different output voltage levels. Modulation index always it is directly proportional to the number of levels. So see the based on that, initially we have 31 level, and based on that we are varying modulation index. We are getting different output voltage levels. So, and again here I have taken again experimental results. If you see here, this is experimental output waveform for 31 level. Again, I have tested with linear loads and non-linear loads. And this is the linear load, and this is a non-linear load. And again, I have tested with the unity power factor to lagging power factor. And during dynamic load changes, the proposed inverter is well stable. So again, here I have tested with the lagging power factor to unity power factor. So this is the way how to so this is a symmetrical multi-level inverter, 31 level inverter. And this is again, I have proposed the symmetrical multi-level inverter. It has been published in IEEE Access. And see that this is one of the structure. This is a basic structure. It will operate with asymmetrical mode. This proposed inverter, it consists of 6 switches and 2 DC sources. We are able to generate 7 levels. This is the expected output waveform. This is the simulated output waveform. This is the expected, that is the experimental results output waveform. So again, by using a basic HBridge inverter, basic circuit proposed asymmetrical multi-inverter, I have implemented with 31 level. This is another structure. And based on this is the switching tables. Based on the switching label, we are able to generate gate pulses. This is the extracted results from the MATLAB. This is results, experimental results, and this is simulation results. This is a simulation THD and experimental THD. So again, I have tested with again here linear load, non-linear load, lagging power factor to unity power factor to power factor. As I said here, see that again here the proposed inverter is well stable during dynamic load changes. So this is another one. I have proposed this with it is also published in IEEE Access, and this is a recently accepted one. So this is another structure. See that this is a basic structure. By employing 3 DC sources and 5 switches, we are able to generate 5 levels. And by employing, as I said here, this is actually basic step. We don't have a HBridge inverter. By using a HBridge inverter, this is a polarity generation. We are able to generate negative levels. So this is one of the structure. By using this, we are able to generate 5 levels. This is the expected simulated output waveform. This is the experimental output waveform. And again, I have added one more switch to the proposed inverter, and we are able to generate 7 levels by having 3 DC sources. So this is a simulated output waveform. This is the expected experimental output waveform. So by using that same thing, again, I have implemented with cascaded with 7 plus 7, and we are employing with 2 more switches plus extra. We are having one DC source. We are able to generate 15 levels. And this is a 15 level simulated output waveform, and this is a experimental output waveform. And again, I have tested with my MLI, 15 level MLI with linear loads and non-linear loads. And again, I have tested with lagging power factor to unity power factor to lagging power factor, and lagging power factor to linear unity power factors. Again, here the proposed inverter is well stable during dynamic load changes. And THD also is, so this is another topology. So recently it is accepted in IEEE access, and I have proposed, so as of now I have implemented with only single phase, and now I have implemented with 3 phase with the different topology. And this is a 19 level proposed inverter. 19 level inverter is, it consists of 4 means 6 unidirectional switches, 7 unidirectional switches, and 2 bidirectional switches. By employing 3 DC sources, we are able to generate 19 levels. This is a 3-phase configuration, and this is a proposed leg A, and so phase A. So again, here this is the expected waveform, and we are able to generate 19 levels. So this is output simulated output voltage. This is the switching table, and this is a 3-phase output voltage waveform. And again, as I said here, again I have tested with linear loads, non-linear loads. So this is this waveform shows that 19 levels, and this is a 3-phase 19 level output voltage waveform, and this is a phase leg A with linear load, with the resistive load, and again motor load, inductor load. There is nothing but inductor load. Again, we have tested with the linear, that is R load to L load, and L load to R load. During this low dynamic load changes, the proposed inverter is well stable. And this is another kind of topology. This is another kind of topology. By employing 3 DC sources and 4 unidirectional switches and 3 bidirectional switches, we are able to generate 9 levels. And this is another structure. This is by by proposing this, and we are able to generate having operating with asymmetrical mode. And this is a simulated result. This is the experimental results. And so I want to increase the more number of levels. I have cascaded with two symmetrical mode, that is 2 9-level MLI, and that is 9 plus 9 is 18 minus 1, 0, we will get a 70 level. So this is the circuit diagram of proposed 70 level MLI, and this is a switching table. So based on that, again, I have extracted the results, 17 levels. That shows that it's having 17 levels. And this is the simulation THD, and this is the experimental output waveform. Again, I have tested with linear loads, non-linear loads. This is the linear load with R load, and this is the non-linear load, and this is again unity power factor to lagging power factor to unity power factor. Again, here the proposed inverter is well stable during lagging dynamic load conditions. Again, THD also calculated. So finally, you can say that it can be a large scale implementation in the grid connected system, agricultural loads, and electric drives, and domestic systems also can implement in order to improve the power quality, the harmonic content, and you can implement this in power system, as well as you can concentrate on pack devices, and you can concentrate on the D-Statcom DVR, and even you can apply if you are employing with a bidirectional inverter. You can employ with hybrid vehicles. This is one of the future strength. And you are able to you can connect this directly to the proposed inverter if you are reducing THD, and you can connect directly to the grid, and you can interface with the DVR. That is also one of the issues. So we need inverter to inject the voltage. So this is a major issue. So as of now, I have concentrated by employing with the reduced number of components with lesser DC sources, by generating higher number of output voltage. So thank you. If you have any queries, please. Yes. Any doubts?
So thank you for the session, sir.
Yeah, sorry for this. I have internet issue or I'm not able to do presentation. Okay, fine. Okay.
It's okay, sir. So I request the participants, if you have any queries related to the presentation, you just post in the chat box, or else you can unmute your mics and you can ask the questions.
Yeah, any queries, please, your side? Any queries? Any queries? How to generate, extract the energy from the solar panels, and how to generate PWM technique to get pulses? Any queries? Yes. No doubts. Thank you. If you have any queries, you can approach me at any time. So I have implemented. I think I have generated 120 level inverter also, but I am not able to show you because it is not published. So the THD is reduced. So please, if you have any queries, you can approach. Any doubts, please?
So I request the participants, if any doubts, you can raise the doubts. Or else you can post your queries in the chat box.
So any queries, please, you can ask, you can send your queries. I think you can take proper direction for your research. As in future, it is going to rule with inverter, with converter for grid connected systems, as well as hybrid vehicles. So please take with the inverter it will play a major role in future. You can design with higher bidirectional inverter or bidirectional converter by having yeah, can you use modular multi-level inverter converters in PV? Yes, you can use. So thing is here, as I said, I think someone is asking a doubt. So you can design by modular converter anything, but you have to extract energy from the solar panel. That is the main issue. So you can use modular multi-level inverter, no issue. Okay, you can use any inverter. The objective is we need to connect to the grid. So that is one of the issues. By having only solar PV, and we are extracting energy from the solar PV, and we are giving to the load. That is one of the issue. But we need to connect to the grid connector. You have to connect to the grid. So then you need to design LNC values, because obviously THD is high. So obviously you need to design effective filter design. So if THD is quite high, so it is very difficult to design your LNC values. It will increase the size also. So getting LNC values is very difficult in real-time implementation. So basically, you can take. My suggestion is you can. I think now you can take a Cefic converter. By having Cefic converter, I think you have secondary side. There is a inductor. By employing with inductor, you can use multi-output output voltage. You can say single input and multiple output. By having inductor there, you can generate multiple output voltage levels by having mutual inductance. Like I have taken one HBG inverter for 27 level inverter by employing with only single DC source. Like that, by having a Cefic converter, output, by using transformers, you can generate, you directly can connect to the HBG inverter or any inverter. Okay. So thing is here, so once again I'm saying you need to test your inverter with the linear loads and non-linear loads. By reducing with the number of components. Even if you reduce one switch, that is one of the novelty. So directly you can connect, no issue. Yes, any doubts? Better to have inverter. Those are having, you can test with your inverter with linear loads and non-linear loads, and with reduced number of components. Okay, I think no queries. Thank you for inviting me, Dr. Kumar and Dr. Sudhir, and my Ramakrishna Reddy is there. Yes.
Sir, good afternoon, sir. I'm Sudhir, sir. Hope you remember,
Yes,
sir.
Yes, sir. Yes, sir. Yes, sir.
Thank you so much, sir, being in our session.
Yes, sir. Yes, sir. Actually, due to internet, I am not able to complete as well.
Thank you, sir. It may have a little glitches, sir.
Yeah.
That is not a big issue, sir. But your session is very helpful for all the people who are doing with renewable energy sources, sir.
Yes, sir. Thank you.
On behalf of participants, I can assure you that they can utilize your valuable delivery about this particular session, topics which you have delivered to the participants. And it's my personal request, sir, in future also, we need your help.
Sure. I see. Whenever you are calling, my hometown is Tirupati only. I'll be there anytime.
Thank you so much, sir.
Okay, no issue. I'll give effectively next time because due to internet, I am not able to give. Still, if you have any queries, please ask. Thank you.
Yes, sir. Thank you so much, sir.
Thank you so much, and thank you, Kumar, inviting me. And special thanks to HOD Sudhir and Dr. Kumar, both of you, and your management, SV Engineering College. So, special thanks to all of you. Thank you.
Thank you so much, sir. Participants, thanks for your patience. And tomorrow we will be having a session on nature-inspired algorithms by Joshi Mano. So please be there on time by 10 a.m. in the morning. Thank you and have a good day. Bye.
Thank you. Bye.
Thank you, sir.
Thank you.
Thank you.
Thank you.